Swayam Prabha. Digital India. Educated India.
So, today we will continue our discussion on the mechanical properties of metals. We have not only metals in today's discussion, but also mechanical behavior of materials as well. So, in the previous class we discussed largely about metals. We will go further into the discussion of metals here, and also discuss briefly about mechanical properties of polymers and non-metals as well. So, basically what we have seen is that the mechanical behavior is the response under different kinds of loading and environment in which loading occurs, because this is a very important aspect, since the mechanical behavior of a material very strongly depends upon the conditions of service, whether the conditions of service are like stress plus temperature, as in case of an IC engine cylinder. So, you have a material that is being subjected to certain internal pressure during the combustion. There is certain temperature which the material is exposed to, and then there are flue gases and many corrosive elements as well, which are present inside at high temperature. So, now the material has to withstand these things, and the mechanical behavior under these three major trying conditions has to be acceptable for a long life of the engine. So, basically when we okay a material for manufacture of an engine or for even a design of an engine, we need to first examine its response under different kinds of loads. So, we examine the response first under only tension, then we examine it under different temperatures. So, basically we try to determine the deformation of the material, the propensity of the material to undergo permanent change in shape at high temperatures. Well, when you talk about an IC engine, you do not want any permanent change in shape to take place at high temperatures. So, you would like to know how much temperature resistance, thermal resistance does the material have, how much of strength the material can exhibit at high temperatures and withstand the pressures. So, basically you need to design the cylinder so that the stresses in the cylinder are much lower than the so called yield point, which we will examine during the course of this lecture. But then yield point is basically a transition between recoverable deformation to irrecoverable deformation. So, recoverable deformation is temporary change in shape, permanent change in shape is irrecoverable deformation, that is plastic deformation. So, yield point is a transition from one state to another state, and one has to be absolutely below that yield point for the structure to remain undeformed even in most trying service conditions. So, we need to understand the response under different kinds of conditions, because you have corrosive elements as well. These corrosive elements try to eat into the material by reacting with the material. So, when the material reacts with the environment, then it loses some strength. So, as a result, the cross section that supports the load keeps on decreasing. So, you take a boiler for example. Boiler also has the same situation or similar situation. You have water inside. So, you have water being boiled at a high temperature and pressure. You have superheated steam being generated, and therefore, the pressure vessel as such is subjected to high temperature, pressure, and the pH of the water is not exactly 7. So, the water is going to react with the body of the vessel, and therefore, some allowance has to be given for corrosion or for reaction of this water with the material which forms the boiler. So, we need to therefore understand the mechanical behavior under under different conditions of loading. Now, these conditions may not be monotonic, these conditions may be fluctuating, for example, right. The loads can fluctuate. Let us say in case of a boiler, you start the boiler, the pressure rises to its operating pressure, it remains steady for a long time, and then when you shut down the boiler for maintenance, again the pressure comes down to its atmospheric pressure. Similarly, the temperature also comes down to room temperature when it comes to maintenance. So, the boiler sees a certain cycle of temperature and pressure. So, temperature rises and so does the pressure. So, these cycles get repeated over the lifetime of a boiler, and so these loads are not always monotonic in nature. So, in a tensile test we obtain the properties of the material by monotonically loading it, that is, we either subject the material to continuous tension or continuous compression. But in case of actual use, there are cycles of loading to which the material is subjected to. It is not just a monotonic loading. Yes, in a short time interval it might look like a monotonic loading. For example, you start the boiler, the temperature and pressure both rise, and then you have loading up to the operating pressure of the boiler, and so this event might look like monotonic loading of the boiler, but then you retain it to a very long duration. So, this is what is the trying situation, because there are different deformation mechanisms which come into play. If something is held at high temperature for a long period of time, even if the yield stress has not been exceeded, still you can have deformation which is time, temperature and activation energy dependent deformation. So, in order to examine the performance or in order to predict the performance of a material, a structural material under different in-service conditions, different environmental conditions, we need to subject it to different stimuli. Therefore, the different loading environments have to be created artificially, and the response of the material examined under single loading condition, under combined loading condition, meaning load as well as the high temperature, load, high temperature and corrosive environment. So, all these things have to be simulated and the response of the material examined, so that you can predict the durability of the material as a boiler material or as an engine material. So, we must understand that the external loading, whatever we apply, it creates stress in the material. So, the response of the material to balance the external loading is in the form of stress, that is load per unit area. If there is no load, there is no stress generated in the material. So, you need to first determine what is the distribution of stress over the entire body of the product. So, what it means is that the design of the product should be such that there should be no non-uniform distribution. So, the distribution of stress should be as uniform as possible, and there should be no so called stress concentration, or there should be no stress razors as a result of the geometry of the product. Now, in many cases, from functionality point of view, from different points of view like weight reduction and things like that, you might have to do with introduction of few stress razors. I mean, you try to avoid them to the extent possible, but it might not be able to you might not be able to eliminate them altogether. So, that is why one needs to find out what is the extent of effect the stress razors are having on the structure, to what extent the stress has gone up beyond the nominal stress which had been used for design. So, when there is a stress, there is a strain. Naturally, there is a deformation in the material, and there are two types of strain. One is fully recoverable strain. Fully recoverable strain means elastic strain, because once you remove the load, the entire strain is recovered. Okay? But then if you cross the yield point, then the strain becomes irrecoverable. So, some strain is permanent. So, the material undergoes permanent deformation under a stress that once you exceed the yield point. Now, what happens to the recoverable strain? Irrespective of whether you exceed the yield point or not, recoverable strain is there to stay. The reason why the recoverable strain is always there is because the atoms have been displaced away from their equilibrium positions. That is what generates the elastic strain, because when you release the load, they tend to come back to their original equilibrium position, and so this results in recoverable elastic strain. So, the stress up to which the strain is fully recoverable is called the yield point. So, we will see how we determine the yield point in case of structural materials, and beyond this point an additional irrecoverable strain is obtained. So, the total strain is a sum of recoverable strain plus irrecoverable strain. So, recoverable strain is called as elastic strain, irrecoverable strain is called as the plastic strain. So, therefore, the strain is a total sum total of elastic strain and the plastic strain. Now, we have different types of monotonic loading. One could be a tensile loading as shown here. So, you have a force acting on the workpiece. There could be bending loads as well. So, here you have a cantilever, and then there is a force acting on the beam like this, and then it causes a bending moment which is maximum at this point. So, because force into length is the bending moment, and that is the maximum here. So, the bending strains, the bending stresses and bending strains are going to be extremely high at this point. Then you have compressive loading. Similar to tensile, you could have compressive loading as well. In fact, many of these manufacturing processes have compressive loading like rolling, forging, extrusion. These are classic examples where the compressive loads are quite significant, and therefore, material behavior under compressive loading becomes very important. Then you have shear loads. You see you have shear loads over here. So, the area remains practically the same, but then there is a change in shape. So, you have tan theta as the shear strain, you have the angle here as theta. So, you have tan theta as the shear strain that is experienced under a certain amount of force. So, when theta is equal to 0, the shear strain is 0, and when you generate some angle theta, then the shear strain increases in proportion to the angle theta. Now, if you look at the elastic regime, you have an absolutely linear relationship between the stress and the strain. So, you have stress and strain. So, you have an absolutely linear relationship, and that is called as the Hooke's law region, because you know that Hooke's law is something that gives you a linear relationship, or which postulates a linear relationship between stress and strain, and that happens because the interatomic distances increase under load, and when you release the load, the atoms are restored to their stable equilibrium positions. So, that is what generates the elastic strain, and that is that's the outcome of this calculation. So, you take the slope of this line, stress versus strain, and then you get the modulus of elasticity. When we looked at the interatomic distance, how interatomic distance is determined, the interpotential curves, what we had said is that the radius of curvature at the trough of the interpotential curve is proportional to the Young's modulus. So, the curvature, not the radius of curvature, the curvature at the bottom. So, if the curvature is very sharp, the Young's modulus is very high. So, the smaller is the radius of curvature, greater is the Young's modulus. So, the interatomic arrangement therefore has got a very significant effect on the Young's modulus that is observed, and therefore, if you take steel for instance, irrespective of the variation in the chemical composition, as long as it is a ferrous material iron based alloy, the Young's modulus does not vary too much. It remains practically constant. So, the difference between the Young's moduli of aluminum and steel is because of the equilibrium distance between the two, and then the interpotential curve that is responsible for, or the shape of the interpotential curve that is responsible for many of the observed properties, and we have seen that in many of the previous lectures. Then we come to a possible stress strain curve where this part there is nothing linear about it. So, the Young's modulus keeps on varying from point to point. So, if you want to find out the Young's modulus at a given point, then you have to draw a tangent, and the slope of the tangent gives you the Young's modulus at that particular point. So, here is a situation where Young's modulus continuously keeps on changing from point to point. But in most metals we have this type of situation. The response of the material is linear up to a point, and then it becomes non-linear once it gets into the plastic deformation range. So, we look at this where the different materials respond differently. Well, so it is no surprise that different materials will respond differently to the same stimulus. So, let us say you have a stress varying with time. So, you have a stress rising all of a sudden very rapidly up to a certain level, remaining constant for a certain period of time. So, I took the example of a boiler, for example, right. Yeah, the stress does not of course increase instantaneously, but then if there is a rapid rise in stress, maybe the combustion in a cylinder, the pressure rise in a IC engine cylinder could be a better example. So, here the stress rises rapidly, maybe it remains constant for a while, and then it drops down. Basically you are giving a stimulus to the material, and the corresponding response is in the form of strain, which also rises, remains constant up to a point, and then comes down. So, so this is the ideal elastic solid which, so the stimulus is the same, but then with the same stress variation, different materials will respond differently with strains. That is what I am trying to explain to you, and that is because of the arrangement of atoms, either in form of different crystal lattices. There is a because of different interpotential curve, nature of the interpotential curve, the shape of the interpotential curve, and the arrangement of atoms in terms of polymeric chains in case of polymers. There are various reasons which go into the atomic arrangement, or basically the interatomic forces, interatomic distance, the electronic configuration of the atoms, which are the root cause for the different behavior in the material. So, two materials, let us say aluminum and copper, and nickel, all of them have face centered cubic structure, but because of the difference in the interpotential curves, they would respond differently to the same stimulus, namely the same variation in the stress. So, here the variation in the stress is on, constant, and off. The ideal elastic solid would show an elastic strain in tune with the increase in stress. So, the increase in stress would be in phase with the increase in, so increase in strain will be in phase with the increase in stress. It would remain constant with the stress, and then it would come down. Now, if we look at the material which deforms permanently, okay, then you see that as the stress increases, the strain increases, and then it acquires a certain permanent set. It acquires a certain permanent set because now the entire deformation is not recovered. So, if you take elastoplastic material, meaning the material undergoes permanent change in shape, then basically what it means is that it has crossed the yield point. After crossing the yield point, it has acquired certain amount of plastic strain, and then that plastic strain is essentially so much of plastic strain remains behind. What is recovered is just the small height over here. So, what is recovered is just the small strain over here. So, the elastic strain recovered is very small here, it does not come down to 0, it remains at a certain level. So, many times this phenomenon of the material trying to recover to its final position of 0 strain is unable to do so because of the plastic strain that has been undergone by the metal, and that is the reason why the overall strain that you see is a permanent strain. So, this kind of thing is used in many applications of practical use. For the same variation in the stress, now you see that there is a non-linear behavior, there is a non-linear variation in the strain, because there is a phase lag between the development of strain and the rise in stress. So, the rise in stress is very sharp, very rapid. For elastic solid it was equally rapid, for elastic plastic solid also it was equally rapid, but now there is a viscoelastic solid, because of viscous effects there is a phase lag between the stress and the strain. So, the stress rises instantaneously as shown here, but the strain does not rise instantaneously to its maximum value. And then when it relaxes as the load comes down, again when it relaxes, then it also does not relax instantaneously, and so this phase lag is introduced because of viscous effects. So, you have instantaneous elastic strain followed by elastic strain which increases with the time under stress and recovers very slowly. So, some plastic flow can also occur, meaning some permanent set in the material can also take place. So, this strain may not come down to 0, it may asymptotically remain at a certain strain level. So, some plastic deformation can be observed. We have rubbers, you have rubbery type of flow where the stress increases and so the strain also increases, and with although the stress is constant, the strain continues to rise. When the strain continues to rise, so in the constant stress region the strain continues to rise, and then it drops to practically 0 when the stress drops to 0. And so, basically the rise and fall of stress, rise and fall of strain is in tune with the rise and fall in stress, but in between when the stress is constant, the strain increases in spite of stress being constant. So, this is something this distinguishes this material from, let us say, an elastic plastic solid, because you have excessive elastic strain plus some non-recoverable plastic strain. So, this small amount of strain is the non-recoverable plastic strain. So, most of the strain is elastic, but then there is a non-recoverable plastic strain coming into play over here. Again you have viscous flow where it behaves like the material behaves like a viscous liquid. So, with time the plastic flow, the strain increases with time. So, when the strain increases with time, we also call it as something like a creep and things like that. So, you have it behaves like a viscous liquid, plastic flow increases with time and small elastic recovery. So, small elastic strain is recovered and most of it is a plastic strain. So, this is very similar to creep flow which is shown over here. Here the only difference is that this is linear. In case of viscous flow there is a linear increase in strain with constant stress, whereas here there is a non-linear increase in strain with constant stress. So, you have a creep plastic strain increasing with time and then after some elastic recovery. So, both are similar, actually both are similar because even in creep there are viscous effects, there is some amount of grain boundary sliding, there is dislocation activity also inside the material, and therefore, you have for the same stimulus a different response of the material in terms of strain. So, the stress variation is the same, the stress rises instantaneously, remains constant over a certain period of time and then drops suddenly, but material response with strain in a different way depending on whether it is elastoplastic, whether it is rubbery, whether it is viscous, or it is a creep type of deformation. And then you have another kind of response. So, we have seen a number of responses with for different kinds of materials. So, this creep response is typically with metals and ceramics above 40% of the melting temperature. At about 50% of the melting temperature, you have some thermoplastics and glasses above glass transition temperature, and some metals about half of the melting temperature show this kind of behavior. So, again this is both these behaviors are very similar similar to creep type of behavior, because viscous flow is again a part of the creep deformation. Creep deformation does involve viscous effects. And then when you talk about rubbery, it is typical of elastomers or rubbers where and thermoplastics at temperatures above viscoelastic range. So, if the temperature is above viscoelastic range, then this is the kind of deformation you see over here. Now, if you look at the polymers, when you look at polymers, you have different kinds of polymers. One is shear thickening with yield stress. So, the material becomes more viscous. So, as you increase the shear rate, the viscosity of the material increases. So, basically, well, normally with Newtonian fluids like water, if you stir it, the shear rate increases, but still viscosity remains the same. So, viscosity remains unchanged. So, the shear rate and viscosity are linked in that a higher shear rate would cause a shear thickening in one type of materials and shear thinning in another types of materials. Typically polymers, thermoplastics which we use for injection molding for instance, they show this shear thinning behavior, because they as shear rate increases, the viscosity continues to decrease, whereas with Newtonian fluids the viscosity remains constant. As you see, shear stress with strain rate, in Newtonian fluids viscosity is constant, which is also the slope of this curve. Here the viscosity keeps on changing, and finally this becomes horizontal, meaning the viscosity is decreasing. So, slope continues to decrease, indicating shear thinning with as response to increasing shear rate. So, this is what different materials do when you are when you subject them to different kinds of stress. So, for a given stress cycle or given stressing history, the strain history depends upon the kind of material, the temperature that you that it sees, and so on. Now, we come to the relative densities, because density is a very important parameter when it comes to deformation. Higher is the density, usually higher is the melting point, and therefore, the capability to withstand high temperature, the capability to remain undeformed at high temperatures is much better when we have materials with increasing density. So, for example, magnesium is a very lightweight material with a density of less than 2 gram per cc. Now, this has a very low melting point. Magnesium has got a very low melting point. Here tungsten is not mentioned, but then tungsten and rhenium, vanadium. So, many of these materials which are refractory alloys, molybdenum and similar materials, these high temperature materials which are essentially refractory alloys have got high density, and they are therefore able to withstand stress at high temperature. So, high temperature creep is withstood by these. Ceramics are oxides and oxide nitrides of different metals, or they are glass, concrete. So, these ceramics are the ones which do have very limited ductility. They have ductility at high temperatures. Glass, for example, melts at high temperature and has got extremely high ductility at high temperature, but at room temperature it is extremely brittle. Polymers are have a different chain type of configuration. So, depending on the structure of the material, the responses which we saw earlier are going to change. So, I mean the secret of the responses which we saw, different responses to a given stress cycle, is because of the configurations, the configuration of atoms in each of these materials, their chemical nature and their properties at different temperature conditions. So, polymers for example are branch chain compounds, or basically these are long chain compounds of carbon and hydrogen, and so basically these exhibit the behavior of the chains unwinding and coming back to their original shape. So, the springiness is not because of interatomic spacing, yes it is because of spacing, but then it is also because of the polymeric chains extending and coming back to their original shape. Similarly, composites also have got the lowest density. In fact, composites were developed for combining the good qualities of metal as well as non-metals. Now, we look at the possible methods of assessing these material properties, mechanical behavior. So, you have the tensile testing machine frame with a extensometer. An extensometer is something that measures the extension. Now, if you do not use an extensometer and rely on the crosshead movement to evaluate the strain or evaluate the deformation in the material, then the compliance of the machine, because when you deform the material, the force is also acting on the machine frame, and under the force which you are applying to this specimen, the machine frame also deforms. So, that is why the machine frame will also elongate, and the elongation of the sample will be partly out of the genuine elongation of the sample and the deformation of the machine frame. So, if you want to exclusively read the deformation of the sample itself, then it is important to have an extensometer, because that will read only the deformation of the sample. So, many times tests are done without an extensometer, taking into account the crosshead movement as the extent of deformation of the material, but then that involves this error of machine compliance. If you want accurate results, if you want accurate measurements of strain, then extensometer is required, and one is able to provide extensometers which work even at high temperatures. So, even if one is conducting a test at high temperatures, an extensometer which will last that or which will withstand that high temperature is available. Of course, they are expensive, but then instruments are available. Now, you have another state of stress like shear strain being generated. So, you have the shear force acting on a given area. So, shear stress is essentially force divided by the shear force divided by this area A naught. The same is true about the tensile stress. So, tensile stress F is tensile stress is determined by the force F acting on an area A naught here again. So, this is a circular area because you have right circular cylinder as this sample shape. So, you have the cross sectional area which is a circle, and therefore, this F by A naught is the tensile stress under uniaxial tension. Here the stress is the shear stress because the force is in a shear force acting on area A naught. Then you have torsional stress and strain. So, you have the torsional stress which is due to the force being applied across this diameter. So, that gives you the torsional stress, and the corresponding strain is the angle phi which is determined at one end. So, if you look at the torsional strain or twist At this point there is 0 twist, and as you go to the top, as you go to the other end of the free end of the cylinder, the torsional strain continues to increase. So, when you talk about torsional strain, there is a gradient of strain from bottom towards the top, whereas in this case the strain is uniform over the entire length. Here the strain again is which is the shear strain is in the form of an angle, and that is also uniform. If you look at the quantities that quantify the mechanical behavior, the stress and the strains, we have what is called as engineering stress and engineering strain, true stress and true strain. So, we were talking about force per unit initial area, and that is the engineering stress, the definition of engineering stress which is given over here. So, this is shear stress force divided by area. Here you have engineering stress force divided by initial area, which is given over here. Now, in elasticity what happens is that the cross sectional area A naught remains unchanged, and therefore, engineering stress and what we call as true stress are identical. What is true stress? True stress is load per unit instantaneous area, load per unit instantaneous area. What is the difference between initial area and the instantaneous area? This difference is very significant in plastic deformation. That is because the volume of the deforming material in plastic deformation remains constant. Unlike elastic deformation, where the volume of the deforming material can increase or decrease depending on whether it is tension or compression, in case of plastic deformation, the volume of the deforming material remains exactly constant. So, as a result, supposing you are elongating this material, so the volume of the deforming material remaining constant. So, the cylinder has got a constant volume. Naturally, as the length increases, the cross sectional area decreases. So, now the decreased cross sectional area is not the same as the initial cross sectional area. So, naturally for the same force and a decreased cross sectional area, the stress is going to be higher. So, F by A is going to be higher than F by A naught in case of uniaxial tension. Why? Because now the area has reduced from A naught to an instantaneous value A by virtue of the volume remaining constant and by virtue of an increase in the length of the sample. So, now we therefore have another metric here, force divided by instantaneous area, which is true stress, and then when we talk about strain, a simple definition of engineering strain is just delta L by L naught, change in length upon original length, which is a very logical and very simple definition of strain. But then when we look at instantaneous area for plastic deformation, we should also consider instantaneous length for plastic deformation. So, naturally you need to have the true strain based on an instantaneous length. So, now what it means is that true strain is ln of instantaneous length by initial length. How this comes about, we will see in the next in the slides to come. We will also do a small calculation to convince ourselves to realize that. But then you have the true strain being defined as ln of instantaneous length divided by initial length. So, this is also called as a logarithmic strain, because this is also called as because the strain varies as a logarithm of the ratio between the instantaneous strain instantaneous length and the initial length. Now, if I am deforming the material in uniaxial tension sigma, I have applied a certain amount of stress corresponding to force divided by this area. Now, if I take a plane which is at an angle theta with respect to this axis. So, this is my tensile axis, and there is an angle a plane which is oriented at an angle theta. The reason why we do this is that we would like to know whether the stress distribution or the stress values change with orientation or not. So, I have a value of stress corresponding to this direction of loading and corresponding to this cross sectional area, meaning this particular plane which is oriented perpendicular to the axis of load. Now, I have a plane which is at an angle theta which is not 90 degrees, but which is at some angle theta with respect to the axis of loading. And now I would like to know whether the stress remains the same or whether it changes. So, the stress variation, the stress on this plane, the normal stress on this plane, similar to this normal stress over here. Okay. So, this is the normal stress on this plane. So, the normal stress on the inclined plane over here is given by sigma cos square theta, sigma into cos square theta. Why? Because now you have two things. So, you have this load divided by area. So, load the component of load is F cos theta in this direction, and this cross sectional area is equal to A divided by cos theta. So, where this is the area A. So, supposing this area is designated as A, then load divided by A is my true stress sigma. On this plane also I have to find the perpendicular component. So, that is F cos theta, which is a perpendicular component of force, and this area is A divided by cos theta. So, this is A divided by cos theta is this area. So, now I have an expression F cos theta divided by A by cos theta, and that gives us the value sigma cos square theta, right. And so, based on our trigonometric relationships, we can also write this as 1 plus cos 2 theta by 2. Similarly, you have a shear stress that is generated, the shear stress that is generated within this plane, and the expression for that is again on similar lines is sigma sin theta cos theta, because now the stress, the shear stress is F sin theta, and A divided by cos theta is the cross sectional area, and therefore, you have sigma sin theta cos theta equal to sigma sin 2 theta by 2. So, now our condition, I mean the stress on this particular plane is a special case here where where theta is equal to 0. So, sigma dash will become equal to sigma, because cos of 0 is 1. So, sigma dash becomes sigma on this plane, but on any other plane you will have a different value of sigma as compared to the sigma which is on this plane. So, that takes us to a plane where the shear stress is maximum, okay, where the shear stress is maximum, because most of the plastic deformation, permanent deformation takes place by shear, right. So, when the angle theta becomes 45 degrees, when the angle theta becomes 45 degrees, then the shear stress is maximum, right, because sin 2 theta is equal to 90. When sin 2 theta is equal to pi by 2, then when theta is pi by 2, sin 2 theta is equal to 1, sin 2 theta becomes equal to 1 when theta is pi by 2, pi by 4 rather. Okay, I will correct myself. When sin 2 theta equal to 1, that is the maximum you can possibly have in terms of the shear stress, and this will happen when angle 2 theta is equal to pi by 2, which means theta has to be equal to pi by 4. So, when this angle is 45 degrees, you have the maximum shear stress. So, that is why you have maximum shear stress theory when it comes to predicting plastic deformation. A structure is said to have failed if the structure undergoes plastic deformation. So, you would like to make sure that the structure does not fail because of maximum shear being I mean the structure being weak under shear. So, you need to find out what is the maximum shear stress acting, the direction of maximum shear stress, and make sure that the material is strong enough in shear and is able to withstand the shear stress on that particular shear plane. So, this is what is shown over here. So, you have different moduli of elasticity and shear modulus, particularly in shear loading here. So, you have the modulus of elasticity and shear modulus being related with in terms of the Poisson's ratio. Now, we therefore examine the features of the response of the material subjected to uniaxial tension. We were talking about a material being subjected to monotonic loading, uniaxial tension. So, first is the linear response in terms of elastic deformation. So, delta sigma by delta epsilon is equal to the Young's modulus, and at some point there is a transition from elasticity to plasticity, but then this is not the yield point. What we have seen is here, although there is a transition from here to the to something else, so this is the elastic limit but not the yield point. So, what is the yield point? Yield point is the one where there is a permanent set of 0.2%. So, 0.2% proof stress is taken as the yield point of the material. So, if you draw a line parallel to the this Hooke's law region parallel to the Young's modulus line, elastic modulus line here, then you will have at 0.2% strain, 0.002% strain. Okay. So, wherever this line intersects, so at 0.002% strain or strain of 0.002, the 0.2% strain, you draw a line parallel to this Young's modulus line, and wherever it intersects the curve, that is your yield point. So, what is this? What is the region between elastic limit up to the yield point? It is a non-linear elastic deformation. So, it is so the elastic limit is essentially called as a proportional limit. Proportional limit means the strain is directly proportional to the stress. The strain, elastic strain is directly proportional to the stress, whereas here that proportionality is not linear. There is some non-linear effects coming into picture between elastic limit and the yield point. And after the yield point, you have permanent deformation, which is plastic deformation, up to a point where you have the so called ultimate tensile strength, where the material undergoes deformation, the dislocation density continues to increase and it cannot increase beyond the point, and therefore a phenomenon called a dynamic recovery takes place, meaning the material loses its work this hardening capability. So, and then it loses its capability to withstand the load. Now, if you look at the elastic and plastic deformation in greater detail, this is a typical curve for mild steel. I mean, this kind of curve is this type of yielding is seen in mild steel, where you have sharp upper yield point and a lower yield point. Usually lower yield point is quoted as the yield point for steels, and then after this the plastic deformation starts. So, you have an upper yield point and a lower yield point, and this is what is called a yield point phenomenon, which is which is also called as static strain aging, and this is responsible for a defect called as Luder's bands. Now, all steels do not cause Luder's bands. In fact, many of the steels which are used for industrial practice do not show this feature at all, but then it has been shown here to educate you on the fact that this feature can appear in the material, and this has to be eliminated, and this once you eliminate this, then you will eliminate the problem of Luder's bands in the components you form on the shop floor. So, ideally speaking, you should not have this, and there are ways and means. Basically people give skin pass rolling or they give a small reduction in cold rolling to address this issue, so that this disappears. So, if you do get this kind of a phenomenon in the material, you need to give a very small 5% thickness reduction to that material, or 5% strain to that material by rolling, so that this phenomenon disappears. Now, most materials which are non-ferrous, I mean which are not steel, which are not based on steel, so aluminum, copper, all of them would show this kind of a behavior where there is no sharp yield point, and that is where our concept of 0.2% proof stress works out. So, here you have this line parallel to the Young's modulus line. This is the proportional limit, and then here is the nonlinear elastic deformation, and 0.2% proof stress is the yield point which is defined for the material. So, now when the material gets deformed in the plastic region, now you see that the cross section goes on decreasing, because as I told you, the volume remains constant, the cross section goes on depleting. So, your loading results in greater increasing stress, the same load, but higher and higher stress. So, what happens is, to balance that, the material has to work harden, because how will the material balance that external loading? It will respond in terms of a higher stress level, right, because the cross section is small. So, high stress level into small cross section will generate the same load that needs to be balanced. So, the stress therefore continues to increase. So, that is why you see that the material is becoming harder and harder, the stress is increasing. So, the stress required to deform the material is continuously increasing. Put in other words, the yield point of the material is continuously increasing. So, if you were to, let us say, unload this material from this strain level, then you will have to strain it, or you would have to stress it to this stress level before it can yield. So, the yield point which you had determined in a static condition, meaning the transition from elastic to plastic in an undeformed condition, does not apply anymore when you go to the plastic condition, because now the material has undergone what is called as work hardening. Work hardening meaning strain hardening. As the strain increases, the material becomes harder and harder. Why does it become harder? Because of the dislocation activity in the material, dislocations multiply, and these dislocations result in increased work hardening of the material. So, the increase in strength of the material results in a stable deformation, because although the cross section depletes, the strength has increased, and therefore, it is able to balance the external load that has been applied. Now, as the dislocation density keeps on increasing, there is a point up to which it can increase, thereafter there is no further dislocation density increase. If you look at the rate at which the material work hardens, if you draw tangents to this curve at different locations, you will find that the material is work hardening at a decreasing rate. So, here just after the yield point, the rate of work hardening is very high, but then as the material goes on deforming, the rate of work hardening continues to decrease, and at some point like the ultimate tensile stress, the rate of work hardening becomes practically 0, and that is because you have a process called a dynamic recovery, which results in the dislocations arranging in specific configurations, in low energy configurations, due to which you have subgrain boundaries which are generated, and there is no further work hardening possible. Now, we have seen in strengthening mechanisms that the work hardening is because of one dislocation blocking the other, or when there is a high dislocation density, the dislocations themselves impede the dislocation movement, and therefore, that helps in work hardening. But then once the dislocations have arranged themselves in low energy configurations like subgrain boundaries, then the hindrance to the moving dislocations is reduced. The extent to which the dislocation can move freely without being obstructed continues to increase, and therefore, the load carrying capability of the cross section decreases, because now the work hardening capability of the cross section is lost, and therefore you have deformation taking place at decreasing stress, and you have what is called as localization of strain taking place as well in a cross section where the strain tends to get concentrated. Why? Because now that cross section is not able to get any further work hardened. So, earlier any cross section was or every cross section was supporting the load. So, the strain was distributed absolutely uniformly, but here the strain is non-uniform because the cross section that is unable to support the load first becomes the section where the strain gets concentrated. Strain concentration means more depletion of area, cross sectional area depletes faster, and when it depletes faster, the stress rate, the rate at which the stress rises increases faster, and that is why the load carrying capacity of the cross section drops very rapidly over here, and then you have a fracture which is called as a ductile fracture or a cup and cone fracture, because during the course of forming, during the course of plastic deformation, there are lots of microstructural features which have developed inside the material. We will see them a little later, but then you have what is called as cup and cone fracture, where the central portion looks fibrous and the peripheral portion, which is called as the shear lip, is relatively bright, and therefore you have two regions, two distinct regions. One is the one is the fibrous zone, and other one is the shear lip. So, this is a typical these are typical features in a ductile fracture, which results after a significant amount of deformation, plastic deformation has been undergone by the material. Now, if you take materials like silicon carbide etc., which are not ductile, which do not undergo plastic deformation, which are brittle for example, which would show this kind of mechanical behavior, you will not see this cup and cone type of fracture, because the features which develop as a fibrous zone will not be developed because there has been no plastic deformation before failure. We will see in subsequent classes on fracture how ductility influences the appearance of the fracture, but then you have ductile fracture where significant plastic deformation has been undergone by the material. Now, I will show you how to determine the yield point, because we have said that 0.2% proof stress is the point at which yielding takes place, material transitions from elastic to plastic. So, now what we get from a tensile testing machine is the load extension curve. So, load extension data is what we get. So, you have positions. So, initial position is 0, no strain. Initial stress is also 0 because there is no deformation. So, you have engineering strain, engineering stress, true stress, and true strain. So, let us see the as the position increases, as the deformation increases, this coordinate increases. So, which means that the length of the sample is increasing, and so is the stress. So, this stress is also increasing, the stress is also increasing. So, if you look at this entire curve here, which is stress versus strain, you have this fairly linear, and this is the point where there is which can be seen as the yield point. Now, you can mark it by judgment or intuition, but then how do you do it unequivocally, because different people might mark the point at different locations, and you see that the scale is also very cramped, very compressed. So, there can be significant errors, significant differences between the judgments of two individuals who might want to identify the yield point, and therefore, we plot a parameter of epsilon minus sigma by E. So, what essentially it means is that in terms of the of this slide which I had shown you, the recoverable elastic deformation, we are trying to find out this. So, this is epsilon. So, this is epsilon minus sigma by E is this. So, epsilon is from here to there, okay, epsilon is from here to there, and sigma by E is from here to there. So, what we are trying to do is that we are trying to subtract sigma by E, okay, which is the recovered elastic strain, from the overall strain. The overall strain is epsilon and sigma by E is the recoverable elastic strain, and what is left behind should be 0.2%, 0.002. So, that is what we are trying to find out. So, when this parameter reaches the value of 0.002, okay, when this parameter reaches the value of 0.002, then you call that as the yield strength of the material. Now, you see that here it is 0.00199, so it is not 0.002, and here it is slightly over 0.002. So, you interpolate between the two and then you get the yield strength as, so you interpolate between these two values of stress 472.18 and 473.23 to get the yield strength of 472.71 MPa as the yield strength. So, you determine the yield point based on the, because up to this point it is all linear in nature. So, what you do is you correlate stress with strain and determine the Young's modulus first. So, first thing is to determine the Young's modulus. You need to take points such that they lie on a straight line. So, basically when you fit a straight line through this stress strain relationship, R square has to be practically 1, and so this is very important. You will see that the Young's moduli in different directions with respect to rolling. So, if you have rolling direction, transverse direction and direction of 45 degrees. So, the yield strength changes, the Young's modulus also changes. So, the properties of the material differ between the rolling direction, transverse direction and the direction of 45 degrees. So, basically this shows you that there is a directional dependence of the Young's modulus and the yield strength as well, and then you therefore calculate the average value. Now, this Young's modulus is something which has not been I think calculated using an extensometer. So, this is 29427 MPa as the Young's modulus. So, you can get accurate values once the measurements of the elastic strains are made using an extensometer. So, I think we have seen some quantities which we can determine using the tensile test, how we determine the yield point and the Young's modulus, and now we will go on to our further discussion on some calculations pertaining to the elastic and plastic deformation in the subsequent class. We will try to solve a few problems in the subsequent class, so that we get a feel for handling the mechanical properties of the material. Thank you.